Well, let's see. It's almost 10:30. One person here so far. Let's see, Ty, I think you're in the group that already did send me your projectile velocity. Is that right? Somebody sent me that. Anyway, let's see if it was.
Yeah, I'm in that group.
Okay. You guys figured it out correctly. I had calculated the velocity too, and it's within just a couple of centimeters per second of yours out on the last decimal place. And I think the variation is probably just where we estimated the center of those dots to be. So,
Yeah, some of them were a little like right in the middle.
yeah. So, yeah, and I sent the angle back. I don't know if it would have reached all of you or not, but you can have another meeting. I need to light a fire under the other groups to get them to do it. I put a new homework assignment up today that'll probably be the easiest homework assignment you'll have. And it's called, what did I call it? Multi-page PDF. And I'll switch over and show you just what it is. And let's see, if I just go to assignments, I'm not sure what the student view looks like on this thing, but I don't know where I put it. Multi-page PDF, here it is down here. The assignment is to turn in a 5-page PDF as a single file, or yeah, yep. Here are the requirements. Use 5 standard sheets of 8.5 by 11-inch paper. You can have other text on them, pull them out of the recycle bin if you want to, I don't care. But at the top of the first page, write your name and page 1, and use a pen, not a word processor for this writing. On the second page, write your birthplace and page 2. On the third page, blah, blah, blah. And so you write a different thing at the top of each page, but each one should say page 1, page 2, page 3, page 4, page 5 as part of what's on there. And then you can use a scanner if you have one, but otherwise use an app on your phone. And I recommend Office Lens because it's free, but photograph the pages one at a time, but don't exit out of the app in between the photographs. Otherwise, you'll end up with 5 individual PDFs. And I want you to have a single 5-page PDF. And then make sure all the pages are full size, right side up, and in the correct order from page 1 to page 5. So this is a skill I would like everyone to develop. And then submit the PDF file below, and there will be a place here for you to submit it. I'm not in student view. Maybe if I switch to student view, you can see what this looks like. Oh, it still doesn't show it. I'm not the correct student or something. But there will be a spot on the assignment page to submit it. And so it's a 20-point assignment, but you don't get credit until it's perfect. So it has to be full size, right side up, and in order. So shouldn't be too bad an assignment. I think quite a few of you did okay on that when you were submitting your tests. So, but not everyone. So it's going to be an easy assignment for some, and some will have learning to do. I'm still grading the tests. It's actually not nearly as efficient to grade tests online as it was back in the olden days when I got a written copy and just had a stack of them I could go through. I got to shut something off here or close the door. Okay. I want to go more with Newton's laws today, and do some problems that are maybe a little bit more challenging. And one of the ones I want to do is for this week's lab, which is something called an Atwood's machine. And I'll make a drawing of what that particular thing happens to be. And what in the world did I do with that thing? Oh well, we'll switch over here to the IPEVO visualizer. And go from there. There it is. So a little later today, I'm going to kind of go through some steps for solving Newton's laws problems, but I'll sort of model it here. And this problem is called the Atwood's machine. And I'm going to start just by drawing a circle, which is, well, actually the Atwood's machines we use have two circles on them. So they've got two pulleys, and oh great, I'll probably end up with a different size circle on each one of these, but we'll see. Those are pretty close. Okay, so these things represent pulleys, and the ones that we have at school are, oh, I don't know, they're probably about that far apart. And then they're very easy to turn. If I flip one of those things with my index finger, one of the pulleys at the end, it'll turn for a long time without slowing down, and it's almost massless. So for this lab, we can ignore the mass of the pulleys and pretend that they're not being accelerated. And then we'll have the floor down here at the bottom. So, and we've got this string hanging over here. And I'll take pictures of it when I actually do the lab and maybe film one in action. But I'd call the mass on this side m sub r for the mass on the right side. And then I'll have a hanging mass on this left side that is m sub l, oddly enough. And m sub l will actually be more than m sub r. So I have to hold my finger under this thing to keep it from falling to the floor. And then when m sub r is sitting on the floor and all the strings are in a straight line, so I don't have m sub l lifted up at all so that the string goes slack, it'll be a height h above the floor. And when I take my hand out from underneath m sub l, it'll accelerate toward the floor. M sub r is accelerating upward at the same rate because they're tied together by a string. And we're going to use this experiment to figure out the acceleration due to gravity. Turns out it slows things down. This doesn't accelerate toward the floor with the acceleration due to gravity because it's resisted by this extra mass over here. And so I'll model a solution here. There's our situation. It's nice a lot of times to have a sketch when you make a solution. And then what I often do is identify what I need to figure out. And in this case, what I want to figure out is the acceleration. So from things that I can measure and time, I'm actually going to time how long it will take this to go from being released to hitting the floor. And so I'll be able to do that. Let's make free body diagrams for these two things. And I mentioned free body diagrams last week. It's the way that you solve a problem like this, and you start by making a dot to represent the object of interest. And I'm going to deal individually with m sub l and m sub r, and then combine what I can. And so for m sub l, one of the forces acting on it will be m sub l g, and that's its weight. And as long as we're doing experiments on Earth, we're going to have this force just about every time. And so that'll be an important one. In fact, probably every time if we're doing Newton's second law problems. Then it's got a string tied to it. And I'll call the string tension that's acting on it T sub L. This is one of our kinds of forces that we have. It actually is due to the electromagnetic force. A piece of the string will loop under a little bit of the m sub l. Actually, m sub l will be a hook that we put masses on, but that's okay. Anyway, it's the electromagnetic force, but it's produced by a string, and strings can pull. They can't push, but they can pull things up, and that's why we have to loop it over a hook so that it can pull. So those are the forces that are acting on this mass on the left side. Now, I've got them written with arrows on top indicating that they're vectors, but in this case I can just say, let's let positive be downward. Now, this is a little bit weird, but the reason I'm going to let positive be downward is because when I move my hand from under here, that's the direction it's going to accelerate. So with positive being downward, and here's how I indicate that. I put a plus sign with a down arrow like that. Then I can write Newton's second law. F net is going to equal m sub L a sub L. And the L's just mean that I'm dealing with the left-hand mass here. Okay, well, what forces do I have? I've got one of the forces is m sub L g. My net force will end up being the positive force minus the opposing force, the negative force minus T sub L, equals m sub L a sub L. And that's as far as I can go to start with, because I don't know T sub L, and I could measure a sub L to figure out T sub L, but we'll just go with what we have here. All right, now let's consider the mass on the right side, and we're going to be interested in the part when the mass has left the floor, so there won't be the floor acting on it anymore. Within about a millisecond of me moving my hand out from under m sub L, this thing will be off the floor, and so we can ignore the floor after that. Okay, well, what acts on m sub r? It's going to have m sub r g pointing down. Okay, that's just its weight. And then it'll have a string tension that's pulling up on it. That's T sub r. And for this one, I'm going to let positive be upwards. I can do that. I can let positive be down for one part of a system. We think of this as a system. And positive be upward for the other part. And the reason I'm doing that is because it's going to be accelerating up. So I'll just do that. And so I'll let positive be upward. And here's how I indicate that. Just a plus sign with an arrow pointing up. And F net on it will equal, this is going to be m sub r a sub r. Now, what's the net force? Well, that's the upward force. Here's the downward force. Because it's accelerating upward, I know that T sub r is winning over the weight of it, and the net force will be T sub r minus m sub r g, and that'll equal m sub r a sub r. Okay, so I have two equations here that I want to deal with to figure out the acceleration. Now, it turns out that I'll be able to combine these two together, and I have to make some simplifications, but here's what they'll be. These two masses are tied together by a string, okay? And if m sub L accelerates downward, m sub R is going to accelerate upwards with a number that's exactly the same. And because of the way I chose my directions, down positive for this one, up positive for this one, they'll both have the same sign of acceleration as well. And so I can say that A sub L will equal A sub R, and I'm just going to call that A. That'll be the acceleration of either one of these things. Then something else that happens to be true in this case is that because, oh, there's a string that passes between the pulleys. It's all one piece of string. I forgot to draw it in. Because these pulleys are so easy to spin, you end up having the same tension in all parts of the string. And we don't care about that tension, but we can say that in magnitude, T sub R is going to equal T sub L, and I'll just call that T as well. Now I'll rewrite these equations. I will have m sub L G minus T is going to equal m sub L A, and for this other equation, T minus m sub R G is going to equal m sub R times A. Okay, this is what's called a system of equations. And we have two equations that are kind of linked together. And the unknowns in these equations are A and T. There are lots of fancy mathematical ways to solve these equations or solve equations like this, but one of them is just substitution. I don't care what T happens to be. So if I solve one of the equations for that, and I'm going to solve the bottom equation, and then substitute that stuff in for T, then T will be gone from the equations, and all I'll have left for an unknown is A. So the bottom equation, I'll solve for T. T is equal to m sub R G minus plus m sub R A, and this is equal to T. I'm just going to stick that into there. And I'm going to come up here, and I will have m sub L G, that's the start, minus T. But this is equal to T, and I'm going to wrap it in parentheses.
Mr. Ham, I can't see what you're writing.
Oh, at all?
Oh, well, I can see what you're, but like what you're writing up there. You have to pull the paper down a little bit.
Oh, okay. Or change my aim a little bit. How's that? Let's see. Now you can't quite see the bottom. Better? Sort of.
Yeah, pretty much.
Okay. We can still see the bottom equation here. And now we're up there. Okay, but anyway, now I'm going to plunk this stuff into there. And I'd have m sub L G minus, and I'm wrapping this stuff in parentheses because I have to distribute a minus sign. And that will equal what's on the right side of that, which is m sub L A. And let's see, distribute the minus sign through. I'll have m sub L G minus m sub R G minus m sub R A equals m sub L A. And this is just algebra at this point, but I'll bring this term with the acceleration in it across because I want to have them on the same side so I can factor the A out because it's the A that I'm after. And I'll be left with m sub L G minus m sub R G equals, well, I won't factor it yet, m sub R A plus m sub L A, which is equal to A times m sub R plus m sub L. And let's see, on the right side, I can factor G out of here, and I'll actually have m sub L G, m sub L minus m sub R times G on the right side. And when I solve for the acceleration, I get this nice little expression. M sub L minus, that was supposed to be an m sub R, minus m sub R times G divided by m sub R plus m sub L. Okay, now this expression may look kind of scary and complicated, but let me tell you about it. This expression on top, actually, if I'd left it as m sub L G minus m sub R G, what it represents is the difference in weights. And m sub L is the part that descends. It's the heavier mass, okay? And so the net force is the heavier mass working against the weight of the lighter mass. And that ends up being what the net force is. But the mass that has to be accelerated by that net force is the total mass, both the m sub R and the m sub L. And what we do in the experiment is we make the masses so they're not that far apart, and that makes the numerator of this thing small, but we make the masses have a fair amount of mass. Like we actually use, altogether, I think we have about 520 grams is the total mass, but the difference between them at most is only about 20 grams. And so you end up with an acceleration much smaller than the acceleration due to gravity, and you can time it very easily because it'll take several seconds or a few seconds for this thing to drop to the floor, even though it's only a little over a meter off the floor when we do the experiment. So it slows things down is what it does, puts them in slow motion. And in this lab, it will be the first lab that we ever do that we'll make a graph for, and we'll take a bunch of repeated data points for varying values of the mass difference. The mass total ends up being the same in every case, because what I'm going to do is just take, I'll drop it first, and then I'll take 1 gram and move it from this side to this side. The mass total stays the same, but the mass difference changes when I do that. And so I'll get a bunch of data points, and then we'll make a graph of the acceleration versus what I call the mass ratio, A versus m sub L minus m sub R over m sub L plus m sub R. And the slope of the graph ends up being the acceleration due to gravity. And so a bunch of new things. And I'll gather all the data out there at school, and probably tomorrow afternoon. I have to be out there to meet somebody. And we'll see how all of that goes. Anyway, so that's an Atwood's machine. And that'll be this week's lab. Okay, something else I wanted to talk about is elevators. That's a classic example of applying Newton's second law. So we'll imagine that we have an elevator here, and it's got a cable attached to it, and in the elevator, we're going to have a scale, and then we'll have our physics student standing on top of the scale there. And we're going to do things to the elevator. We're going to imagine that maybe the elevator is going upwards, going downwards, accelerating upwards, accelerating downwards. So we'll look at a bunch of different situations here. So for the first situation, let's imagine that the acceleration moves up with constant velocity. So whoops, the elevator moves up. Okay, now I'm going to make a free body diagram that's going to work for every one of the situations that we have here. And this free body diagram is for the person who's standing on the scale. Okay. Well, one of the forces on them is mg downward. That's their weight. And then the other force that acts on them is the force that the scale exerts upward on them. Okay, they're standing on the scale. They are not standing on the floor of the elevator. This force is an electromagnetic force. It's the repulsion between the atoms in the bottom of their shoes and the atoms in the top of the scale. And when you stand on the floor, the force you feel is due to the repulsion between the atoms in the bottom of your shoes and the atoms in the top of the floor. Okay. This ends up being what you perceive as weight. Okay. It's actually the third law partner. This is the force the scale exerts on you. It's the third law partner of the force that you exert on the scale, and the scale reads the force that you exert on the scale. So if we can figure out what this happens to be, we can find out what the scale's gonna, it is what the scale is gonna read, but it's also what you will perceive as your weight when you're on the scale like that. Let's suppose we'll just give this person a typical student mass of, let's say, 65 kilograms. Okay. Well, we can figure out what their weight is going to be on Earth. W equals mg. Now, it may not be what the scale reads, but if you weren't accelerating, this will be what your scale will read. It'll be what you perceive as your weight if you're standing on anything. And so 65 kilograms times, we'll just go 9.8 meters per second squared for this. And this student's weight is going to be about 640 newtons. I know they're newtons because they're kilogram meters per second squared, and that's what a newton is. So 640. And I just rounded that to two significant figures. I actually get 637 newtons, but I don't have that many sig figs. So 640 newtons there. That's what we have. All right. And by the way, that would be about 140 pounds. So just for comparison, we can equate newtons and pounds, but we can't equate kilograms and pounds because they're two different things. They weigh two different things. All right, so we have the elevator moving up with constant velocity. Okay, well, in that case, on all of these, I'm going to let up be the positive direction, I think. So positive is up, and I'll have the force of the scale up and mg down, and I don't, actually it's the same free body diagram every time, so it doesn't matter. But I would get the force of the scale minus mg, that's going to equal the net force acting on them, because these are the only two forces that we have to worry about, and that'll equal ma. But if they're moving up with constant velocity, the acceleration is 0. So in that case, we just have the force of the scale will equal mg. Okay? The scale will read their weight if the elevator is moving up with constant velocity. The same thing would happen if the elevator was moving down with constant velocity. I'd have a net force of 0, and the force of the scale would equal mg. So for example, or situation 2, elevator moves down, constant velocity. Again, we get that the force that the scale exerts on them is just going to equal mg. Albert Einstein was well known for looking at simple situations and figuring out profound things from them. And for a while, early in his career, just after, let's see, he got the job 2 years after he graduated from college, and he'd had a hard time getting a job because he didn't make good impressions on his professors in college. And in those days, it was pretty much letters of recommendation was what got you your jobs. And he did not get good letters of recommendation, but he got this job as a patent expert 3rd class in the patent office in Bern, Switzerland. And he did some amazing things in his first few years there, but after he'd been working there about 5 years, he had this, what he called the happiest thought of his life. And he said, I was sitting in my chair in the patent office one day, and I realized if I were in free fall, I would not feel my weight on the chair. So let's put this elevator in free fall. Okay. So this will be the case where the elevator accelerates downward and actually I'm going to start with just a downward acceleration of A, and then we'll let that downward acceleration equal G. So what we'd have in that case, we still have the same free body diagram, but this time we would have the force of the scale minus mg is going to equal an actual ma in this case, but if it's accelerating downward, I'm going to put a minus sign on this. So that's what that minus sign indicates, that it's accelerating downward. And in that case, the force that the scale exerts on the person is equal to mg, add mg to both sides, mg minus ma. And so depending on how rapidly it accelerates downward, they're going to feel lighter during that time. If you've ever taken a fast elevator, if you ever go over to Seattle and go up in the Space Needle or one of the taller skyscrapers, when an accelerator first starts downward, you get this little bit of butterfly sensation. Seems like your stomach is coming up or something like that. That's because you're experiencing a lower weight for a very short time. Accelerators or elevators don't accelerate downward for very long. They just do it for a couple of seconds, and then they move downward with constant velocity. And so most of the trip, you're going to just be feeling your regular weight on the force of the scale. Your feet will feel that. But for a short time, you'll feel a little bit lighter at the top of the downward trip. Now, if A is G, and I put a minus sign on it, so what you would feel is the force that the scale exerts on you would be mg minus mg. That's 0. You would feel weightless. And that's where Einstein got this idea that he would not feel his weight on the chair if he was in free fall. So if somebody took you, lifted up you and your chair to the edge of a skyscraper and dropped you off, you wouldn't feel a contact force between yourself and the chair on the way down. You'd feel weightless. There's some ancient bad joke about some guy being either being thrown off or falling off the Empire State Building, and as he's passing the 40th floor, somebody says, "How's it going?" And he says, "Great so far." He feels weightless. So that's the situation in that case. You actually could feel weightless there. Einstein took this idea and used that as the starting point for his theory of gravitation, which has actually replaced Newton's theory of gravitation, except the math of it is horrendous, and Newton's works just fine in most situations. But we call that theory of gravitation the general theory of relativity, and it may be just about the single greatest accomplishment ever by any physicist, was to figure that out. He was doing it on his own. So pretty amazing. All right, now suppose the elevator accelerates upward. So okay, well, in that case, we would have the force that the scale exerts minus mg is going to equal ma with a plus ma, because upward is the positive direction. And I'll have to slide this up just a smidgen. The force that the scale exerts, is it still showing? Not quite. That'll work. Is going to equal mg plus ma. And that's going to be greater than your weight. In that tall building, when you get on the elevator at the bottom of the building and start upwards, your knees almost buckle a little bit, because for a brief instant, you feel heavier than your actual weight by this amount. Now, elevators in public buildings are built in such a way that it's never that much more than your regular weight. It's just a small difference, because they don't want getting sued to be sued by people whose knees buckle when they got on the elevator. But still, that's the situation that would happen in that case. So those are the elevator problems, just about every situation you can think of. And you could put numbers in here for the acceleration, but if you understand the concept and how to set up the equations like this, you'll be pretty well off. So, but do solve problems. Okay, what did I do with those things I printed off? I'll post this thing in the in the example problems for today, but we'll be working on these tomorrow as well. These are problem-solving strategies for Newton's laws of motion, and pretty much all of chapter 4 and 5, this is what we'll be looking at. And identify the physical principles involved. And in chapter 4 and 5, it's almost always going to be Newton's laws of motion. Sketch the situation. I did that here with my elevator, and I did it with the Atwood's machine. Use well-labeled arrows or things like that to represent all the forces acting, Now, I didn't show the forces acting here. I tend to put them on a free body diagram. And so that's what we want. In this case, the thing that we wanted to determine was the force that the scale exerts on the people or the person. Carefully determine the system of interest, draw a free body diagram of the system of interest and all the external forces acting. Okay. We're going to gradually add more forces to these problems. In this case, it was just the scale and the person's weight were the only two forces, and it was a nice one-dimensional problem because everything was going on in the vertical direction. But soon we're going to be adding some horizontal forces that may depend on some of the vertical forces. And so things will get a bit more complicated. We'll drag crates across floors and put the rope attached to the crate at an angle and stuff like that. But we'll learn how to deal with that, get used to making free body diagrams and trying to identify the forces. And then we apply Newton's second law to solve the problem. If it's one-dimensional, we can treat them like scalars. That's what we just did, made it one-dimensional, and with Atwood's machine. Let's see. In 2 dimensions, we need to select a set of axes. That's an XY coordinate system. And we usually choose those axes to minimize the work we have to do. So I am nothing if not lazy. I'll usually look for an easy way to solve the problem, although I don't always find the easiest way. I have sometimes done problems. I'm not afraid of algebra, I guess, and I don't mind doing things in a way that might be algebraically complex. And sometimes I need to get reined in a little bit. I remember, I was teaching over at Edmonds Community College before I got this job. And this one day I'd done this relative motion problem in a very complicated way. And took about a page or a page and a half of algebra. And then one of the students said, couldn't we just do this? And I thought about it and said, yeah, we could. Let's do it that way instead. And it was about 4 lines of algebra. So it was much easier. But anyway, and then check your solution to see if it's reasonable. And this is something that's hard to do at first. You need a little bit of experience with it. But if you're looking at things like car speeds, for instance, things you should know is that 60 miles per hour is about 27 meters per second, and 90 miles per hour is real close to 40 meters per second. So if you're looking at a car speed and you end up with a number like 512 meters per second, you probably made a mistake, because that would be over 900 miles an hour. Your car would be breaking the speed of sound. And but it's hard to know when you're first starting off with problems if your answers are reasonable or not. So it may just take some practice. So let's try one more problem and then we'll stop here. This one has us first calculate the tension in a vertical strand of a spider web if a spider of mass 8 times 10 to the minus 5th kilograms hangs motionless on it. Okay, well, I can make a free body diagram for the spider. And here's what it'll look like. I'll have the mass of the spider times g, that's the weight of the spider. And then that weight is being supported by a vertical strand of spider web. And so it'll have a tension in it. And because this is one-dimensional, I can do this as a one-dimensional problem. I can do it as a scalar problem. And I'll just let positive be upwards in this case. and my net force will be the difference between these two forces. F net equals T minus the mass of the spider times G. Something that points up gets a positive sign. Vectors that point down get a minus sign. And the spider is being supported by this. It's not accelerating upwards or downwards. And so that's going to equal 0. The net force is 0 when the object is not accelerating, because F net equals ma. So the tension is just going to equal the weight of the spider. M sub s g, I'll just plug in the numbers here. 8.00 times 10 to the minus 5th kilograms, and 9.81 meters per second squared. It's not going to be much. It will be. It's interesting. We actually have 3 significant figures on the mass of the spider. That seems a little crazy. I get about 7.85 times 10 to the minus 4th newtons. Okay, now this is actually about 10 times as big as this. Okay, because I multiplied by something that's about 10. It's actually 9.81 times as big as that. And so when a number with a negative exponent gets bigger by a factor of 10, that negative exponent changes from a 10 to the minus 5 to a 10 to the minus 4. So that's something good to keep in mind. Something like that. Now, part B on here is harder. It says, calculate the tension in a horizontal strand of spider web if the same spider sits motionless in the middle of it, much like the tightrope walker below, and the strand sags at an angle of 12 degrees below the horizontal. Okay, I need to draw a new picture for this. However, for the free body diagram, I'll still have the mass of the spider times G acting downward, but now the spider web is going like this. I've got one part going in this direction and one part going in this direction, and on both sides there is a 12-degree angle. I need to start a new piece of paper for this. This is complicated. And I know you probably can't read the problem anymore, but here's the idea. I'll draw the horizontal here. And right in the middle here, we've got the spider, mass of the spider times G acting downward. There'll be a part of the spider web goes this way, and I'm going to call that T sub R, because it's the tension on the right side of my diagram. And the angle it makes is 12 degrees. And then there's tension on the left side too, and it's actually supposed to be symmetric whether I draw it that way or not. T sub L, symmetric means the same left or right. And this is also 12 degrees. We haven't done a problem like this before. This is two-dimensional. However, there's still no acceleration, and so the net force is equal to 0, but I should probably stick an arrow on that, looking like that. Okay, so there's part of the solution. I have a free body diagram, and I would expect in magnitude, and this will be the case because it's right in the middle of it, T sub L is equal to T sub R, and I'm just going to use a T to stand for that. As vectors, they are not equal because one points to the right and the other points to the left. But as scalars, they are equal to each other. Now, here's the thing. When I have a bunch of forces adding together, it must be that the vertical components of the forces are equal and the horizontal components of the forces are equal. Well, T sub r, I can write as an x component. This is T sub r in the x direction, and I'm going to use my x hat notation, plus T sub r, whoops, that's T sub r x, T sub r y in the y direction. But here's the thing, I can draw a picture to represent these things. This is 12 degrees. This would be T sub r x. This would be T sub r y. Does that look kind of like the velocities in a projectile motion problem? The x component will end up being this times the cosine of 12, and this will end up, that's supposed to be a t. This thing will end up being this times the sine. And so if this is t up here, which I said it could be, T sub r x will equal T cosine of 12 degrees, and T sub r y will equal T sine of 12 degrees. Now over here on the left, I'll get something that looks very much like that, except that the x component on the left is going to have a minus sign. And so T sub Lx is going to be the same magnitude as this one, but it points to the left instead of the right. So I'll just call it minus T cosine of 12 degrees. T sub Ly, it points up just like T sub Ry does. And so it'll also be T sine of 12 degrees. Okay, now this is kind of scary so far, but I figured out the components of my tension, which is the thing I don't know. I know what the mass of the spider is and what it is times G, but the tension is what I don't know. However, I could look at the thing you can do with vectors is I would have F net as a vector thing is going to equal MA is going to equal 0. Okay, well the net force ends up being T sub r as a vector plus T sub L as a vector plus mg. Now I've got plus signs on every one of these things, which is okay. I would say that G as a vector points downward, T sub r and T sub L point in their particular directions. But something I can do is that since these forces combine to 0, I can say that F net in the x direction is going to equal 0. Well, mg has no force or no component in the x direction. What I get out of this is I'd have Fr in the x direction, T cosine of 12, plus TL in the x direction. That's just going to be minus T cosine of 12. Those are equal to 0. And all that tells me is that the left and right components cancel out. So, but the vertical components, the net force in the y direction, F net y, I'll get, have to stop right after this, I would get T sine 12 plus T sine 12, I'm running out of space, minus mg. Those are the three forces acting, the upward component of this, the upward component of this, and the downward component of that, minus m sub sg is equal to 0. And we end up with, let's see, this will be 2t sine of 12. Sorry, we're getting sloppy here. 2t sine of 12 degrees is going to equal the weight of the spider, or the tension. If I divide both sides by 2 sine of 12, the tension will equal the mass of the spider times g divided by 2 times the sine of 12 degrees. I already calculated the weight of the spider back here a ways, I think, somewhere. There it is. It's mg was 7.85 times 10 to the minus 4 newtons. So but if I divide by 2 times the sine of 12, remember to wrap this in parentheses when you do it. I've still got that number saved in here, divided by 2 sine of 12, another parenthesis, and I get actually it's 1.9 times 10 to the minus 3rd newtons, which is quite a bit more than this 7.84 times 10 to the minus 4th newtons. In fact, if I divide by it, it's about 2.5 times as much. This amount of tension is quite a bit more. Okay, that was a lot for today. And we'll move on from there tomorrow. And I should have your test back to you, but check out that 5-page PDF assignment and see how good you can do that. And you get multiple tries at it. I think 3 tries before you should expect you may get it perfect the first time. But if you don't the first time, I'll let you know. Tell you what to do about it. Okay, I'll stop that sharing and see you tomorrow. And let's see. It'll be a couple days before I post the lab for this week. I won't be getting the data for it till tomorrow afternoon, but anyway, you should have your tests back tomorrow, so I'll be working on those. And there will be an assignment you can do on that one to turn in solutions for the problems you don't get full credit on, and you can make up some points that way. So I'll talk to you later.